Last video, we built the language of sets, operations, partitions, and the Cartesian product. Now we put that language to work. A function is a special kind of relation, and it is the bridge from sets of outcomes to numbers we can compute with. In this video, we define relations and functions, meet the domain, codomain, image, and preimage, sort functions into one-to-one and onto, and finish with the indicator function, our first real taste of probability. Recall the Cartesian product, all ordered pairs with a first entry from x and a second from y. A relation between x and y is simply any subset of that product. When a pair belongs to the relation, we say x is related to y. Think of it as any bundle of arrows from x to y. A function is a relation with one extra rule. It is single-valued. For every element of x, there is one and only one element of y it points to. None is left without an arrow, and none has two. That unique partner is written f of x, and the rule that produces it is called the rule of correspondence. Two sets come with every function. The domain is the set it is defined on, the allowed inputs. The codomain is the set the outputs are constrained to lie in. We write f maps x to y. Strictly speaking, a function is a triple: the domain, the codomain, and the graph, that single-valued subset of the Cartesian product. The picture and the formal triple say the same thing. Here is a concrete example. F maps the real numbers to the real numbers with f of x equal to x squared. The rule of correspondence is x maps to x squared. The image is the set of values the function actually attains, all the f of x as x ranges over the domain. It is a subset of the codomain and need not fill it. Going the other way, the preimage of a set T is the collection of all inputs that land in T, every x whose output lies in T. The most useful case is the preimage of a single value, called its level set. All the x that map to that one value. And here is the crucial fact. The preimage of a single value can contain many arguments. Take f of x equal to x squared. Draw the horizontal line at height c. It meets the parabola at minus root c and plus root c. So the preimage of c is 2 points. One output, several inputs. Hold on to this picture. Pulling a value back to the set of inputs that produce it is exactly how a random variable will work. A function is injective or one-to-one if it never sends two different inputs to the same output. Distinct inputs, distinct outputs, no collisions. A function is surjective or onto if its image is the whole codomain. Every target value is hit by at least one input. Nothing is missed. A function that is both one-to-one and onto is a bijection. Every output is hit exactly once. And that is exactly when an inverse exists. The inverse maps y back to x, undoing the original, and the preimage of every value is a single point. Here is the function that opens the door to probability, the indicator function. Fix a subset S of the universal set omega. The indicator of S maps omega to just two values, 0 and 1. For an outcome omega, the indicator is 1 when omega is in S and 0 when it is not. It simply reports whether its input belongs to S, 1 for yes, 0 for no. When omega is a sample space, that single 0 or 1 readout is the seed of the Bernoulli random variable, which we meet in full later in the course. Step back and look at what Chapter 1 assembled, because every piece reappears in a probabilistic guise. The universal set omega becomes the sample space of an experiment. A partition of it underlies the law of total probability, breaking a question into disjoint cases. The preimage of a function is the mechanism behind random variables, and the Cartesian product lets us describe several quantities jointly. So the set theory was never a detour. It is the scaffolding the whole subject is built on. With sets and functions in hand, we are ready to start counting, which is exactly what the next chapter, combinatorics, is about.